Hello, so in this video I want to talk about the solution to the two-dimensional diffusion equation. The thing is, up to now we've only been considering the one-dimensional case. So in other words, we started a particular point, and we can either move right or we can move left. So we're moving in one dimension, right? Because a dimension is just, if you like, a line where you can only move kind of either right or left. Okay, so right or left is one-dimensional. Well, a two-dimensional case is now we're incorporating up and down as well. So we're incorporating another line which is perpendicular to that. So we can move left or right, that's one dimension, but we can also move up or down as well. So we can also move up and down as well, okay? And so that's what's known as the two-dimensional case. And I think, because we've kind of looked at the solution to the one-dimensional case, how do we find the solution to the drift diffusion equation? Well, we found a solution to a simplified version of that, which was the diffusion equation. I say simplified; it wasn't actually that simple, but it was a simpler version, and then we could use that to find a solution to the whole thing. Okay, well now likewise we can use the solution which we found to the diffusion equation for the one-dimensional case and find a solution for the two-dimensional case. So in other words, we can build on it. It's a bit like Lego bricks. Yeah, once we've kind of got the core of it, once we've got the core solution, we can then build on it and adapt it to our specific case. Okay, so that's effectively what is going on here. So let's just remind ourselves of what was the solution to the one-dimensional diffusion equation. So yeah, here was our our drift diffusion equation. So in other words, if we basically all the situation that we can have in the one-dimensional case, so we can either move left or right by any amount that we like. So we can move more in the left direction than in the right direction, and that's taken into account of the drift term, and the speed at which we do that is taken into account of with this term, which is known as the diffusion term. Well, basically, if we're moving in equal parts, left and right, so we're not kind of more biased to move right than left. So, for example, there's not food on the right, for example, so we're not more likely to move to the right. Then therefore we can reduce this down into something known as the diffusion equation, which is just simply this. So it's getting rid of that drift term because we're not more biased to move in one direction than the other. And this is what's known as the diffusion equation in the one-dimensional case. Well, in the two-dimensional case, it's kind of the same thing, except we not only just move kind of in the x direction, so we no longer just move in the x direction, but we can also now move in the y direction as well. So we can also move up and down. So we can move left and right, and we can also move up and down as well. So therefore, we're not just going to have this derivative. We're not just going to have the derivative with respect to x. We're also going to have the derivative with respect to y as well. So the second derivative with respect to y as well. Okay, because then that takes into account the second derivative of all our directions that we can have. So the second, this is the second derivative term, and it's the second derivative of not just x, but also the other direction we can move, which is y. Okay, so this is the diffusion equation in the two-dimensional case. Okay, and what is the initial condition? Well, the initial condition in the one-dimensional case was this. It was given by this. So in other words, the probability that we're going to end up at some position x, which again just lies in this one-dimensional plane. This one-dimensional plane, it can lie anywhere in this one-dimensional plane, but only in this plane. So anywhere in this plane at a particular time particular time t, was given by something called the Dirac delta function. The Dirac delta function, and this is what this thing is, and it's Dirac delta function in terms of x. Now I'm not going to try and draw out what the So the Dirac delta function was this. Okay, this was the Dirac delta function at a particular time point x. So this was Dirac delta function at a point x. Well, now we're moving in two dimensions. Therefore, we're going to have to incorporate an extra dimension in here. So we're not just moving in the x direction, we're also moving in the y direction as well. So therefore, we can have a Dirac delta function, not just in the x direction, but also in the y direction as well. So the Dirac delta function in the y direction is essentially going to be a little bit more complicated to draw, but essentially it's going to be a 3D plot. Let me just try and draw this in. It's something like that. Okay, so effectively these are my dimensions which I'm defining, and let's say I start at this point over here, just for clarity point. Then it's just going to be a spike. It's going to be a spike, and everywhere else is just going to effectively be zero. So it's going to lie in this what's known as I suppose an XY plane, and this is just my Dirac delta function. This is my Dirac delta function. So it's just going to be some spike, effectively, and everywhere else is going to be zero. So everywhere else I'm going to lie in this plane. Okay, it's an infinitely large spike. This is what the Dirac delta function is going to look like, something like that, anyway. So this is my Dirac delta function. So this is, if you like, my initial conditions now in my two-dimensional case. So these are my initial conditions in my two-dimensional case. Okay, and if you remember that my solution in my one-dimensional case was like this. So this was the solution to my one-dimensional case, one-dimensional diffusion equation case. Well, now again, I'm just going to introduce my extra dimension. So therefore, I'm also going to have to introduce an extra dimension in here. So it's not just going to be plus x squared. It's also going to be plus y squared as well. It's also going to be plus y squared as well. Okay, so it's going to be x squared plus y squared in there. Okay, and that's all there is to it. So that is the solution. So basically, you know, like I say, I just consider the one-dimensional case and what I had for the one-dimensional case. Then I can easily apply it to my two-dimensional case. Notice as well, I can equally apply it to my n-dimensional case. My n-dimensional case. So let's say, for example, that I've got an n-dimensional case, and I'm just going to represent it as my vector. So in other words, my vector is going to be like x1, x2, whatever. So if I have n different dimensions, okay, and each dimension is represented by n, x2. So each one of these elements in here represents a different dimension. It's not overly applicable here because, you know, we tend to use these models in real life. So the most that we'll ever end up using is probably 2 dimensions. We might end up using 3 dimensions at the most. You know, we won't generally end up using 4, 5, 6, 7, n different dimensions. The most dimensions we'll probably end up using is 3. And most of the time we'll try and simplify it down to 2 dimensions anyway. But if we wanted to, we could. So in other words, we have probability of this thing. So I'm introducing my dimensions, okay, is equal to 1 over 4 pi dt square rooted, e to, this time it's my my modulus, so my vector squared. Well, that's just going to be a modulus, right? That's just going to be a modulus, yeah, because it's going to be symmetric across all dimensions, okay, effectively, over 4 dt. So I'm just replacing that with the modulus because, of course, it's going to be symmetric across all dimensions. You know, I'm going to have n different dimensions, okay, so when I square it, it's a bit like well, what is the modulus of a vector x? So say if my vector was x equals xy, okay. Well, you know, this case here, so I have x squared plus y squared. Well, that is like the square root of that is a bit like the modulus of that. So it's a bit like the modulus squared. Okay, so it's a bit like the modulus squared. So if I square that side and square that side, then that thing is just going to be the modulus squared. Okay, so that's effectively all that's going on there. Okay, so that's the reason why it's modulus. But again, you know, it's not overly applicable for that case. Not overly applicable for that case. But obviously, as we move forward through time, this is effectively what's going to happen. So we're going to end up with something like that. Okay, something like that and something like that. So it's going to be a 3-dimensional case. So we're going to end up with a spike. That's for kind of diffusion and time low. Okay, and then basically as we head forward through time, we're going to spread out a little bit more. But again, this is going to be a 3-dimensional plot. So something like that. Anyway, you know, you could probably find a load of diagrams. There's loads of diagrams in the lecture notes. Okay, but effectively, yeah. Once you've got the one-dimensional case in your head, you can get the 2-dimensional case quite easily.